the comparator op-amp is very simple device, but it has a problem. It has a problem with the noise. So when the input is a very fluctuated input, so means that the input is not a fixed value, it's not a solid line, solid waveform. So it has the noise. Okay, this is the input with the noise. Overall, you can see the shape of the input is a sine wave, but this is not it's not a clear or solid sine wave. It has a noise here. Okay, so if the input is superimposed, this is the superimposed with noise. This will cause a false triggering. What is false triggering? False triggering happen at the region nearby the reference. So when the input has the value, if the value of the input is close to your V reference, so since you have a noise here, the noise is a fluctuated signal, so you can see the switching from plus VCC to negative VCC. So this is happen. It's not is you can see this is not a stable. It's not a stable condition where the output will switch from plus VCC and minus VCC due to the noise. So this is what we call a false triggering. False triggering. So this type of false triggering is not desirable. For example, if you want to turn on let's say you have the aircon, and then you want to turn on the aircon when the temperature exceeds a certain when the temperature exceeds certain your set temperature. So when you have the fast triggering, so when you have the fast triggering, the output of op-amp will give you not a stable voltage to the compressor of op-amp. So this is not good for the actual application. So you need to remove this fast triggering. Okay, false triggering. So how to do that is by using a Schmitt trigger. Okay. So this is our second and last example of this course, which is Schmitt trigger. Okay, Schmitt trigger is a comparator. Basically, this is a comparator with a positive feedback. Okay, positive feedback. Okay, this is the example of positive feedback where there is connection between the output with the V plus. Because since this is a comparator, so the comparator basically compare the V plus and V minus. We want to compare the V plus and V minus. So in this context, your reference point is this V plus. This V plus will become your reference point. You need to calculate the reference point or your transition point. So what is the value of V plus? How we can get the V plus? So we can analyze the V plus using the KCL. So let's label the current first. Okay, let's say the current, this is your I1 and this is your I2. So you have here this KCL here is I1 and I2 both entering, I1 plus I2 equal to 0, and I1 is V reference minus V plus over R1, and I2 is V out minus V plus over R2 equal to 0. So you get here V reference R1 plus V out R2 minus V plus. So this is R1 plus R2 over R1 R2 equal to 0. So at the end, your V plus is equal to R1 R2 over R1 plus R2. So this is V reference over R1 plus V out over R2. Okay. So this is the equation of your V plus. So take note here. This one. Okay, the V plus Okay, V plus value depend on V0. Okay, V plus value, this is as function of V out. And then you know the V out of the comparator have a two possible voltage, which is plus VCC, and another possible voltage is minus VCC. So means that your V out V plus also will have two value. So the first value is when the V out is equal to plus VCC. So this is R1, R2. For R1 plus R2. Okay, so this is the first equation for V plus. The second equation for the V plus is R1, R2, R1 plus R2. Okay, this second condition is where the V out is equal to minus VCC. So you got this is the minus. Okay, so this is the will have the two value. So means that the transition point for this circuit have two transition point. So the first transition point is a high transition point, and then this is the lower transition point. So this is what we call a VUTP, voltage upper trigger point, and this is your VLTP, voltage lower trigger point. So VUTP will trigger only when your current state, your present V out is equal to plus VCC. And VLTP is triggered only when your present V out is equal to minus VCC. So this is how basically the analysis of the Schmitt trigger. Okay, this slide summarize the equation for the VLTP and VUTP. Okay, I want to emphasize on the calculation of VUTP and VLTP. So I would recommend you to derive what is the VLTP and VUTP instead of memorizing the equation. Because when you memorize the equation, so sometimes you don't know, you mix up whether R1 is here or R1 is here. So it's better for you to be able to derive what is VUTP and VLTP. Okay, the flow is quite simple. You just apply the KCL, and then you will have the V plus as a function of V out. And then you know the V out will have two cases when the V out is plus VCC or V out is minus VCC. The V out equal to plus VCC is the case where the V plus is VUTP, and when V out is equal to minus VCC is the case when the V plus is equal to VLTP. Okay, so to explain the operation of the Schmitt trigger, let's do this example. We consider that Vin is a sine wave with the amplitude of Vm, and VUTP is plus Vm of half of the Vm, and VLTP is minus half of the Vm. Draw the output waveform and transfer characteristic. Okay, let's draw the input first. So the input here, the maximum is Vm, this is minus Vm. Okay, so this is your input. So this is your output. Okay, this is the axis for the input, and this is the axis for the output waveform, and this is the transfer characteristic. Transfer characteristic is output versus input. Output versus input. for the input here, the maximum input voltage is Vm and the minimum is minus Vm. So you need to take note on here. This is your Vm and this is your minus Vm. Okay. For the output of the comparator or Schmitt trigger, so it depends on your plus VCC and minus VCC. Okay, in this case, the plus VCC is not given, so you just use this the symbol. This is plus VCC and this is your minus VCC. Okay, so the output is the maximum. The output of the comparator or Schmitt trigger is either plus VCC or minus VCC. So this is your plus VCC and this is your minus VCC. Okay, so also the Vout is VCC and this is your minus VCC. So this is the labeling. We have done with the labeling. So we can do the next step is drawing the transition point. So for Schmitt trigger, it has two transition point. Okay, the first transition point is VUTP. VUTP. So now we assume that VUTP is Vm's half of the Vm, and VLTP is this is minus Vm2. Okay. So we have drawn this one. So we can also take note on, can put it here in the transfer characteristic. So this is Vm2 and this is your minus Vm2. Okay. To draw the output waveform, you need to be clear of the initial Vout value. So what is the initial Vout value? So let's consider when the initial Vout value is plus VCC. So it will start from the VCC. So when it starts with the VCC, so your initial value of output voltage is plus VCC. So the trigger point for this case, because the Vout is plus VCC, trigger point is this VUTP. So VUTP will become the trigger point. Okay, in this case, it will go to the V minus at this point because it is trigger, so it will transition or switch to the minus VCC. So this is at the output. So at the transfer characteristic, what happened? So we start here, V in is 0, and then it go towards the higher voltage. So this is the initial point here, and then it is it go here, the V in is increased until it reach the trigger point. When it reach the trigger point, it go to the V minus. So this is the flow. Okay, next we go now the Vout, the state of the Vout is minus VCC. Okay, the state of the Vout is minus VCC. When the state of the Vout is minus VCC, the trigger point will become, the VLTP will become your trigger point. So although you reach the or meet the VUTP, but it is not, the VUTP is not the current trigger point. The current trigger point is VLTP because now the value of Vout is minus VCC. So what happened? It will ignore this transition point, and the next transition point is VLTP. So okay, so this is what happened at the output voltage. Okay, for transfer characteristic, what happened is at this point, will increase towards the maximum value here at the peak of the input, and then it will go back, reverse. When it reverse, it will not switch to the plus VCC at the Vm/2, but instead it will go back to the 0, input is 0, and then it will only switch back when it reaches the minus Vm squared. Okay. So this is the transfer characteristic. Okay, so now the Vout is, the current state of the Vout is plus VCC. So the transition point is the next VUTP. So this is the transition point. Okay, so this transition point can be ignored. So what it do, it is switch here. Okay, switch here. Okay, so the transfer characteristic is, after it's switching, we'll go to the minimum value, minimum peak, and then it will go back until, and then it will go back and it will finish the cycle, and then it will switch back when it reaches the Vm plus Vm/2, half of Vm. So this is the final answer for this example. So now we have drawn the Vout and we have drawn the transfer characteristic. Okay, for the Vout, the waveform of the Vout, what you need to be aware of is the value of the maximum Vout is plus VCC and the minimum value is minus VCC. So it is a square wave, and then make sure that you take note on where does the transition happen. Okay, where does the transition happen? The transition happen depend on your current state of the Vout. If your current Vout value is plus VCC, your transition point is VUTP. So search for the closest VUTP and that will become your transition point. If your current state of the Vout is minus VCC, so your next transition point is VLTP. Okay. As for the transfer characteristic, so for in terms of the labeling, so you need to be aware that the Vout value is, the maximum is plus VCC and the minimum is minus VCC. For the input, the maximum is the amplitude, the peak of the input signal. In this case, this is Vm and minus Vm. So the transition happen at the VUTP and VLTP. So you need to label the VUTP and VLTP in the axis of the input. Basically, the shape of the transfer characteristic is always like this. So if you label the transition point correctly and then draw something like this, so your answer is correct. Okay, this slide summarizes the Schmitt transfer characteristic of Schmitt trigger. So this is Vout, also Vin. So in this case, your VLTP and VUTP is a positive value. So this is also possible because it's possible by changing the supply DC at your, by changing this V reference value. Okay, this show when the Vin is lower than VUTP, Vout is equal to plus V saturation. Okay, so you can read the slide. See the slides, just explain it again, what I have described in the previous slide. Okay, so there's a one keyword that related to the Schmitt trigger, which is the hysteresis. What is hysteresis? Hysteresis is a properties, means a device behave differently when the input is increasing from the way it behaves when the input is decreasing. Okay. If you see this transfer characteristic, so you have arrow here. When the input is increasing, it will switch at the VUTP. If the input is decreasing, it will switch at VLTP. So this will cause a hysteresis. Okay, in other words, the output will switch when the input increase to one level, but will not switch back until the input fall below a different level. Okay, so means that the switching happen based on your present state. So it is desirable characteristic because it prevents the comparator from switching back and forth in response to the random noise fluctuation in the input. So hysteresis value also have the value hysteresis voltage, the parameter of hysteresis voltage. Hysteresis voltage is the difference between your VUTP and VLTP. So VUTP minus VLTP. So you can just ignore this equation. As long as you can calculate VTP and you can calculate VLTP, you can do this subtraction. So VTP minus VLTP will become your hysteresis voltage.